Our objective in the next few videos is to define precisely how to integrate an n form on an n-dimensional manifold. So these n forms on n-dimensional manifolds are also called top degree forms. Dimensional manifold, they are also called top degree forms or volume forms. So the idea now is to somehow define an integration of such forms on the manifold. Now before we get to this, we must first understand why these n forms, these top forms, are the right integrands that we should be expecting. After all, when we defined integral on curves, we were able to do it very well for just functions, which are not one forms. Functions are zero forms. So we were able to define the integral of a function on a one form. On a one manifold. You must have also seen integration of functions on surfaces when you studied multivariable calculus. So the question arises, why is it that something similar doesn't work? In fact, the integration that you saw for surfaces in multivariable calculus, there itself this theory of differential forms is there hidden in plain sight. So we will get to that in a few videos, but before that, let's try to understand how to find the area of a surface S in R3, how to find area, and how to miserably fail at finding area by taking the simplest approach. So let's say you have a surface and you want to find its area. Well, the natural thing to do would be to approximate this surface by some nice polygons and take the sum of the areas of the polygons, and as you increase the number of sample points on the surface, you would intuitively think that the sum of the polygons, area of the polygons, actually converges to the area of the surface. This seems like a natural, straightforward extension of the definition of the length of a curve, where we just broke up the domain, which is just a closed interval, into various partitions, finer and finer partitions, and said that the curve has a length if the supremum of all such things, all such lengths of polygons, not polygons, length of rectilinear parts that you get, not rectilinear, polygonal parts, the sum of all lengths of polygonal parts that you get that approximate the curve, that has a limit in some sense. So why not try to do the same thing? Why don't you just sample a lot of points on this surface and then maybe just draw triangles, because triangles are the simplest and most flexible polygons. Let's just triangulate the manifold, or in this case a surface, something like this we keep doing. So here we have successfully managed to break up at least a portion of the surface by a union of triangles. You would think that if you repeat this process by making the points closer and closer, the sum of the areas of the triangles will in fact converge to the area of the surface. But this intuition fails miserably. What can happen is, because of the flexibility of 3 dimensions, even in the case of a cylinder, it can happen that these triangles that we are considering, by choosing the points, the vertices in a particular way, you can make these triangles jut out. That means these triangles don't become tangential to the surface. We learned way back in kindergarten calculus that the secant lines of the graph get closer and closer to the tangents. That's essentially what we were using to define rectifiability of a curve, the same idea, that eventually when you sample the points close by to each other, the secant lines become closer and closer to the tangent line. Unfortunately, this doesn't happen in higher dimensions. Here is an example of an object called the Schwarz Lantern. here is, to be more precise, here is a paper model of that. This paper model was not made by me. It was made by a mathematician by the name of Evelyn. Okay, so this is a cylinder, and as you can see here, these triangles are jutting out. By carefully choosing the vertices of these triangles, it is possible to make the area of a cylinder as large as you want. So this derivation, the more precise details, you can find in Wikipedia and the references in the Wikipedia article on the Schwarz Lantern. So essentially what happens is just sampling points on the surface and triangulating the surface is not going to approximate the area. You can see these triangles all jutting out and not being tangential to the surface. Okay, so this approach fails. Approach number 2, and this approach is more in the spirit of what I have been emphasizing throughout the course. Linear phenomenon is easy to understand, non-linear phenomenon are not. So what we do is the following. Now I am going to take the general case of a manifold itself. There is no additional complexity created by going to higher dimensions. So let's take M subset of Rn, a smooth manifold. A smooth manifold. Now by definition, this M can be locally parameterized. So let's draw again. When I'm drawing, I'm going to draw 2D pictures only. So let's say I have a local parameterization. Okay, so you have this map phi, you have point A, and you have phi of A. So pieces of the manifold can be parameterized by a mapping that has very nice properties. It is full rank and so on and so forth, so many conditions. Now we will do idea number 2, which is still motivated by idea number 1. This set U, this open set U, which is the parameterizing domain, you break it up into small boxes. Here these boxes are just rectangles, but in higher dimensions they will be genuine boxes or cuboids. Okay, so let's say this A happens to be in this particular box. Now if you just look at the image of this grid vertices on the manifold, they will be distorted in general, but you can expect something like this. They will be distorted because phi could be non-linear. They will not be straight lines, but they will in some sense form a grid on the local piece of the manifold. Now if you just look at the vertices and try to look at the these small things and try to compute the areas and then sum up the areas of those, we are going to miserably fail, just like the triangle case. Same intuition, it may not be possible for these to be always tangential. It might happen that they will start jutting out and all hell breaks loose, and you get something that is arbitrarily large also. But wait a minute, why do we need to worry about these small pieces not lying in the tangent space? Ultimately, the entire philosophy of the course is, when you have a complicated nonlinear object like phi, just replace it by d phi, which is a linear map. D phi is a linear map, right, at the point A. So the tangent space is supposed to be a good linear approximation of the manifold at a point. The tangent space of an open set in Rn is just Rn itself. Instead of trying to somehow make these grid pieces become tangential, why don't you directly make the thing tangential by definition? So instead of considering phi A of each box, why not consider d phi A of the box? D phi A is linear, a box is nothing but a parallelepiped, so d phi A of the box would be a parallelepiped. This will be a parallelepiped pipette sitting in T phi m. This will be a parallel pipette sitting in T phi m. Okay, so net upshot is we have got a box, or rather a parallel pipette sitting in the tangent space. We know how to find out or measure this parallel pipette sitting in the tangent space. How do you do that? Well, if V1 to Vn span this parallel pipette, then you can of course consider omega of V1 to Vn, right? You can just consider omega of V1 to Vn, where omega is a top degree form. So imagine that omega gives you the value of or it measures the volume or area of parallel pipettes sitting in the tangent space. We now look at the tangent space obtained by taking d phi a of boxes and act omega on that. So the essential idea of integration now reduces to the classical idea of partitions. What you do is you continuously keep breaking down the domain into smaller and smaller grids. Look at d phi a of the boxes and look at omega of V1 to Vn, where V1 to Vn span those boxes, and then just take the sum as these partitions become smaller and smaller, and hope that what you get would be the area or volume of this piece. Okay, so we are treating omega as a generalized density which allows you to measure area or volume. Okay, so that is why I kept saying that differential forms are like densities, and they are the natural objects which you can integrate on manifolds. However, things are not so rosy. When I'm vaguely explaining stuff, things might seem to go well, but there are a lot of problems. Manifolds only have local parameterizations. So we have to break up the manifold in some nice way and define the integral. Break up the manifold into pieces to define integration. So we have to integrate separately on each image of a local parameterization and somehow patch all those together. Of course, it could happen that several local parameterizations, the images intersect. What do you do in the intersection? How do you not double count, or how do you take care of things? So we'll have to deal with that. Second is a more subtle issue. The way I have defined it, if V1 to Vn spans this parallel pipette, then omega V1 to Vn will give you a number. Well, not quite. I mean, it does give a number, but if V1 to Vn spans this parallel pipette, so does V2 V1 ... Vn. Let me just interchange two of them. Now if I take omega of V2 V1 ... Vn by the alternating nature of differential forms, I will get a negative sign. This will give me a negative sign compared to the previous one, right? So it isn't clear which basis you choose for that image parallel pipette. Do you choose V1 to Vn or V2 V1 Vn? There will be a possible sign change. So given two parameterizations, two different parameterizations of the same piece, what is the guarantee? Guarantee that the integrals will be the same the integrals will be the same if I use either of these parameterizations to do the integration process. Integrals will be the same under the two parameterizations. Will be the same under two parameterizations. Even for just the square, which is spanned by E1, E2 in R2, if I had instead chosen E2, E1 and chosen the determinant as the 2 form, then determinant of E1, E2 and determinant of E2, E1 are +1 and -1 respectively. Therefore, there is an issue. We have to somehow decide which of the bases to choose. To do that, we will prefix a basis for every tangent space, which is supposed to give you the choice of bases you have to make. So we have to go on and define what is called the orientation of a manifold. So we are now going to begin the process of addressing these two obstacles. The second obstacle is addressed by fixing an orientation for the manifold, which will tell you the choice of bases to take. The first problem is fixed by the good properties of the Lebesgue integral. So for the next few videos, I'm going to assume familiarity with Lebesgue integrals in Rn and the change of variables formula for the Lebesgue integral in Rn. I will eventually post videos about the Lebesgue integral in Rn taking an elementary approach. So if you're not familiar with the Lebesgue integral in Rn, you could consider postponing watching the next few videos after I talk about the Lebesgue integral eventually. This is a course on real analysis and you've just watched the video on the idea behind integration.